All right, ladies and gentlemen, welcome back. We're going to talk a little bit more about some mathematical models today. One of the ones we're going to talk about right now is called the Gaussian Model. You may have probably never heard of this, but maybe you heard of the other thing it's normally referred as, which is a normal curve or a normal distribution. Okay, and that actually is something that is very, very important to statistics. Okay, basically what a normal curve, what a normal distribution does is it kind of is a way to compare certain things that are normally distributed is what it's called. So this is kind of the shape of it. It kind of makes this sort of bell curve shape. Have you ever heard of a bell curve? Okay, and what it does is it shows whatever you're looking at, the average falls in the middle, and as you go further away from the middle, that is how many things should fall in each of those things, each of those areas. So for example, as you get further away from the average, less and less of that thing should be able to fall there. So for example, like this one's about the SAT and SAT scores, okay? If the average SAT score, I think, is around like a 520, 518, something like that, less and less people are going to score really, really high above that, okay? So if you think of, like, if this is about 500, let's say, 600 might be here, you know, we might have, okay, this is the amount of people that are going to score between 500 and 600, and then out here might be 700, and then 800. You know, it's just going to be less and less people as you go, as you get further away from that average. Same thing on the other side, as you get further away from the average. Again, less people are going to score, let's say, a 400 or 300 or 250 or really, really low scores. Less and less people are going to do that as well. Most people expect to be around the average. So that's kind of what a bell curve does. It shows us, here's kind of the amount of people, and we can figure out odds of people that fall in each of these areas as we go further away from our normal curve, okay, from the middle of it. So here's an example. The SATs in 2014 filed the Gaussian model of y equals 0.0035 e to the blah, 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 all this stuff, where x is the score for mathematics between 200 and 800. Okay, so in the SAT math exam, the lowest grade you get is a 200. The highest grade you get, if you get a perfect score, is an 800. We're going to start by graphing this in Desmos to figure out what the average SAT score was, and then we're going to look at my score. I say I got a 720. I did not take the SAT in 2004, but let's pretend that I did. We're going to estimate what percentile that falls into. Okay, so let's go ahead. Let's jump over to Desmos real quick. Nope. Let's discard this. Okay, so we're going to jump over to Desmos really quick. And we're going to go ahead and we're going to take a look at this normal curve. Okay, so we're going to type this equation in. So the equation is y equals 0.0035 e to the negative x minus 518 squared divided by, oh, I don't want that to be divided by, this divided by, there we go, divided by 25,992. Okay, and then we're going to, as you can see, I can't see anything. I have to change my scale here. So let's go ahead and let's change the scale. We know that our possible score ranges are from 200 to 800. Okay, so we're going to look between 200 and 800. And then in terms of our y's, whenever you're doing one of these normal curves, they're showing really, really small numbers, and you'll see what kind of what we're going to talk about in a moment here. But we're going to go between 0 and 0.004. Okay, and that should again. Oh, something went wrong in my equation. Let's see. I don't actually know what's wrong with my equation. Oh, I put this in there. There we go. All right, there we go. That's what I wanted. Okay, let's reset this. So 0 or 200 to 800. All right. Okay. Now we're cooking with gasoline. All right. We want this from 0 to 0.004. Okay. So here is our normal curve. Okay, here's the normal curve. You can see it looks kind of like that picture I drew over there. And again, the average is going to be what's directly in the middle, basically where this peaks out. That x value is going to be our average. So we can see, look, our average was 518. That's the average on the SAT, okay? So we expect about 50% of people to do worse than the average and 50% of people to do better. And obviously, more people are going to do around the average, okay? Whereas as we go out, it's going to be smaller and less people are there, okay? So we actually want to think of what we kind of refer to normally as the area under this curve is representing the amount of people that are falling in the percentages of people, all right? So if we say that Mr. Guy scored a 720, we want to find 720, so that's going to be about here. And we want to think of what percent of the area from this point under is going to be there, and that would kind of tell us what percentile or where this score falls and how many people we expect that to be better than, okay? And so I can see from it falling about there, I would say, about 80 to 90% of people would be below that, right? Remember, we have to include all the areas, all this room up here and under. I'd say probably about 90% of this curve is below that score right there. So we would say that score is probably in around what we call the 90th percentile, okay? And that's sort of the estimate we're going to make. With the Gaussian models, we are not going to be getting super in-depth mathematically with calculating things. It's going to be more that sort of looking at it in Desmos and making an estimate, making some sort of statement about what we see when we go in there, all right? The next one we're going to use is called a logistic growth model. If you look at the picture of this one on page 423 in your book, what you're going to see is this is one where it grows and starts to look like it's growing exponentially, and then it kind of tapers off and curves out. And we actually have a real good example of that going on at the time of recording this during the coronavirus. But this actually is the example that they use in the book about a virus spreading, because this is normally how viruses spread. They start by spreading exponentially, and then as there are things that sort of make the virus start to taper off, whether that be social distancing measures or a vaccine or whatever kind of interrupts it, the virus starts to taper off and slow down in its growth and not grow nearly as fast, okay? So we're going to give an example of a college campus. There's a highly contagious virus. The virus is modeled by that equation right there. And T is time, and Y is the number of students that are infected. If the college decides that, hey, 40% of students have this virus, we're going to cancel classes, when would they need to cancel? How many days would we expect to go by? T is time in days, by the way. How many days would we expect to go by before, hey, we got to cancel classes, okay? So what we're going to do, okay, is we're going to figure out, all right, when are we going to need to do this? And one of the first things we have to do is figure out what 40% of 5,000 is. So we're going to be doing 40% of 5,000, so 0.4 times 5,000, and that's going to get us 2,000, which is going to be what our Y value is going to be. So we're going to say that 2,000 is going to equal the 5,000 over 1 plus 4,999 e to the negative 0.8t. Okay? What I'm going to do here is I'm actually going to do some cross multiplication. I'm going to pretend this is over 1, and we're going to cross multiply these. Okay? So after we cross multiply, we'll get 2,000 times that 1 plus 4,000, all that e, equals 5,000. I then divided by 2,000. I got 5 over 2. Subtracted 1 from each side. I got 3 halves over here now, 4,999e, whatever. Divided by that 4,999, that gave me 3 over 9,998. And now we have the e by itself, and we can take the natural log of both sides. Negative 0.8t equals the natural log of 3 over 9,998. I then divided by negative 0.8, ended up with 10.14. And remember, that is in days, okay? So basically, based off what we saw here, we can expect that in about 10 days, maybe a little over 10 days, but pretty much in that 10th day, that's when the college is going to say, all right, we have to shut down. We have too many students who are spreading this around. We need to do something to help lower our numbers and maybe start to get it to even out and make it more show that logistic model. All right, so that's that model and how we would go through and solve it. The key thing to remember is because the variable a lot of times that you're solving for is in the denominator, this cross multiplication idea is going to come up where it's like, all right, I got to get this out of the denominator. How can I do that? Well, if I cross multiply, it'll move out and be nice for me. Okay. Last one is a logarithm model or logarithmic model. Basically using a log to model something using a log equation. One example of that is actually the Richter scale, which is used for earthquakes. You ever heard of that before? It's actually a logarithmic model. It uses logarithms to show the intensity of an earthquake. Okay. And what's cool about that is that if you think about the shape of a logarithm, right? So this is a logarithm. Okay. So when we think about the shape of a logarithm, it kind of starts to lower as you go out, right? It kind of starts to go down as you go out. So in terms of a earthquake, the way they do it is that the x, or your input, is the intensity, right? This is the intensity, while the up and down, the y, I'm misspelling intensity, okay? Whereas the y is actually the Richter score, the R score that it gets. So as you get up to those higher R scores, like a 7 or an 8 or a 9 or whatever on the Richter scale, it means it has to be exponentially more intense before it even gets to go up that. Okay, so the difference between a scale 2 or 3 on the Richter scale is not even close to the difference between an 8 or 9 on the Richter scale, right? A 2 to a 3 is like a little bit different in the earthquake. The 8 to the 9 is exponentially more intense. So as you get to those higher levels on the Richter scale, it means a lot more when something gets a higher score. So one example is that in 2004, there were 2 earthquakes, one in Sumatra and one in Alaska. And the Sumatran earthquake had a Richter scale of a 9, while the Alaska one had a Richter scale of a 6.8. Now, those seem like they're somewhat close, like, oh, they're 2 away on the Richter scale. But let's see the difference in intensity, okay? What's cool about this one is I have IO in here. That's the intensity, the minimum intensity, which is just 1. So really this equation is just to get your Richter score. It's the log base 10 of the intensity. So it's pretty straightforward in terms of what you're doing here. So if I put in 9 here, 9 equals the log of I. If I want to solve for I, I'm going to take 10 to each one, and I'm going to get 1 followed by 9 zeros as the intensity. Okay, that's a lot of intensity. That's a really, really large number, 1 billion as our intensity. Okay, that's going to be a big deal. Now, what about for the other one, the 6.8? Well, let's go ahead and let's look at what that one's intensity is going to be. Again, on the Richter scale, it looks like it doesn't look like it should be too far off of the one that was in Sumatra. Okay, and so we're going to go ahead and we're going to plug in 6.8 over here. And for that one, again, I'm going to raise each side to the 10th power. Now for this one, obviously, I don't know what 10 to the 6.8 is. 10 to the 6.8 is off the top of my head. So let's go ahead and let's type that in and see what we get. And we're going to get, if I'm rounding here, we're going to get 6, 3, 0, 9, 5, 7, 3. Okay? So the intensity of that one was about 6 million as compared to 1 billion for the other one. Okay? And you can see that's a huge difference, and that's the reason why that Sumatra earthquake actually caused a lot of destruction. We don't really talk about this one in Alaska all that often. Okay? So that's a logarithm model, just using a log equation. We know how to solve logs. Doing that to solve. Okay? Thank you all for watching. More information on models.